Have you ever wondered how an AI, actually learns anything? How it goes from making totally random guesses to mastering something really complex? Well, it's not magic, it's math. And right at the heart of it all is this one beautiful algorithm that's basically the engine for all modern AI. So how in the world does this engine actually work? So, really, the big question is this. How does an AI learn from its mistakes? I mean, how does it know which way to go to get better, to get smarter? That's exactly what we're going to break down right now. Okay, so before we jump into the solution, let's really get a handle on the problem itself. What's the fundamental challenge that every single AI model faces the second it starts training? I want you to picture a brand new neural network. It's basically a blank slate, right? When it starts out, its predictions are completely random. Seriously, think of a student just wildly guessing on their very first test. The whole learning process then is about one thing: slowly, methodically correcting those initial guesses one mistake at a time. But that begs a huge question, doesn't it? If you're just guessing, how do you know what to change to make your next guess better? And maybe even more important, by how much should you change it? This is where gradient descent comes in. The best way to think about it is like a GPS for learning. It gives the model clear, step-by-step directions toward the right answer. To really make this idea click, we're going to use a super simple but really powerful analogy that just perfectly captures what's going on here. Okay, imagine this. You're on the side of a huge mountain, but you're surrounded by this incredibly thick fog. You know you need to get to the lowest point, down in the valley, but you can't see it. So what do? Well, you'd probably feel the ground right around your feet, figure out which direction slopes down the most, and then take a small, careful step that way. Then you do it again and again. And that is a brilliant illustration of how gradient descent works. The mountain itself is what we call the cost function. It's just a measurement of how wrong the model's predictions are. Your position on the mountain is the model's current set of guesses. And the goal, of course, is to get to the bottom of the valley, which represents the lowest possible error. Every little step you take is gradient descent tweaking the model to reduce that error. So that's the big picture idea. Now let's get into the nitty-gritty. How does the algorithm actually take these steps? It all comes down to a really simple four-step loop. Okay, it breaks down just like this. Step 1, you calculate the error. That's just a number that tells you how wrong the model is right now. Step 2, you find the gradient. Now this is the key. The gradient is basically an arrow that points in the direction of the steepest uphill slope. Step 3, adjust the weights. But wait, we want to go downhill, right? So we take a small step in the exact opposite direction of that gradient arrow. And finally, step 4, repeat. You just do that over and over and over again, taking one step at a time until your error pretty much stops getting any better. And this slide right here visualizes that whole four-step dance perfectly. You can see we start with an initial weight that gives us a really high error. Then with each little orange dot, the algorithm calculates the gradient, takes a step, and lowers that error. And notice how the steps get smaller and smaller as the slope gets flatter? That's the algorithm zeroing in on the minimum cost. It's this journey from being completely wrong to being as right as it can possibly get. Now, while that core idea is pretty straightforward, in practice, there are some really critical choices you have to make that can totally change how well and how fast your model learns. The most important choice of all is the learning rate. Let's go back to our mountain analogy. The learning rate is just the size of the step you take. Are you taking tiny, little, cautious shuffles, or are you taking giant, confident leaps down the mountain? The size of that step is absolutely crucial. And this slide shows you exactly why that choice matters so much. Look at that first graph. If your step size is way too small, you'll eventually get to the bottom, but it's going to take forever. It's safe, but it's incredibly slow. Now look at the third one. If your step size is too big, you'll literally jump right over the solution, bouncing back and forth and never finding it. But that middle graph, that's the sweet spot. When the learning rate is just right, you get down that hill efficiently and land right at the minimum. Finding that balance is a huge part of what makes AI work in the real world. Another big choice is how much data you use to figure out your next step. As you can see here, there are basically three main flavors. You could use your entire data set to calculate the slope for every single step. That's called batch. It gives you a perfect direction, but man, is it slow. Or you could go to the complete other extreme, SGD, and take a step after looking at just one example. It's super fast, but your path down the mountain is going to be really noisy and chaotic. And that's why almost everyone uses mini batch. It's the perfect compromise. You get the speed of SGD with some of the stability of batch. It's the best of both worlds. And you can literally see the difference in their paths right here. Batch takes this smooth, direct, almost boring route to the center. SGD is all over the place, zigzagging like crazy on its way there. And then you have mini batch, which is that nice compromise. It's got a little bit of a wobble, but it moves toward the goal way more efficiently than batch and much more directly than SGD. Okay, so let's zoom all the way out. We've seen how it works, but why is this one algorithm so unbelievably important for the entire field of AI? So what's the big takeaway? It's actually really simple. Without gradient descent, neural networks are just static. They're stuck. They can't learn. This algorithm is the active ingredient. It's the mechanism that lets a model get better with experience, adopt when it sees new data, and ultimately unlock solutions to incredibly hard problems, from recognizing faces to understanding human language. And that leads to the statement, which is just spot on. It truly is the engine. You know, all the other stuff in deep learning, the crazy architectures, the giant data sets, they're like the parts of the car. But gradient descent is the engine that actually makes the car move and go somewhere useful. And what's really important for you to take away is that if you understand this one concept, this simple idea of walking down a hill to make your mistakes smaller, you've taken the first and most important step to understanding how today's most advanced models, like the large language models and transformers that are changing everything, actually work. It all comes back to this. So now you know the secret of how AI learns. But knowing this opens up an even bigger question, doesn't it? If a machine can figure out the best solution to a problem all by itself, what problems should we be asking it to solve next?